Hey y'all, welcome to lesson 122 of the DP Chemistry curriculum. Today we're doing structure 3.2.7, which is an HL topic. We're covering all of it. It's quite a long section. We're talking about stereoisomers, which have the same constitution, so atom identities, connectivities, bond multiplicities, but different spatial arrangement of atoms. We're going to describe and explain the features giving rise to cis-trans isomerism, recognize it in both non-cyclic alkenes and 3 and 4 carbon cycloalkanes, so ring structures. Furthermore, we're going to move into optical isomerism and draw stereochemical formulas showing tetrahedral arrangement around a chiral atom. We'll explain that. We'll describe and explain a chiral carbon atom giving rise to stereoisomerism with different properties. And lastly, we'll recognize a pair of enantiomers as non-superimposable mirror images from 3D modeling. Now, we're not doing EZ system of isomerism that used to be on DP. It is not anymore. And furthermore, we're going to use terms chiral, optical activity, enantiomer, and racemic. Furthermore, knowledge of the different chemical properties of enantiomers will be limited by the fact that they behave differently. And lastly, we'll use stereochemical formulas using the wedge dash representation for enantiomers. Now, before I go through this, I will let you know I already had recorded and wrote the notes for the first half of this section, realized my recording was bugged, and so I'm not going to be taking notes on the first half. I will be going over the notes I've already done. So you may need to pause it more to take those notes if you're doing that on your own. With that said, let's jump right in. So what is stereoisomerism? Basically, the easiest way of thinking about it is the same structural formula, but different spatial arrangements. With stereoisomerism, we break it into two sections. We have cis-trans isomerism, which is the one that I've already done all the notes for, so you're just going to have to pause and go through them. This comes from a carbon-carbon double bond or a ring structure that locks position around those carbon atoms. Optical isomerism, on the other hand, uses chiral carbon centers, which we will fully explain, and I will go through that one with you. I have not done the notes on that yet. So, with cis-trans isomerism, let's start it off. To do this, we have to think about pi bonds. They allow for free rotation. If you think about your ball and stick model of carbons, and I can actually draw this now, we have generally this kind of like ball and stick model linked by these little plastic rods. And when you look at this tetrahedral structure, you can rotate these around. The ball and stick model represents that really well. But the minute you add a pi bond in your ball and stick model, that rotation becomes locked because that bond now consists of two sticks that will not twist between each other. In fact, they're usually bowed from the tension between them. And so that rotation no longer happens. This is a restriction of movement. That means that this top group is always on the top and the bottom is always on the bottom. And if you have two different groups, those will always be top, top, and bottom, bottom. Furthermore, if you think about your ball and stick model and you make a ring structure, this locks movement through the ring structure itself. So you can imagine a piece of paper that has a top side of lines and a bottom side of squiggles. No matter what you do, the bottom side will never become the top side. You can try and twist the paper, which will probably rip it, but it will never actually change to be the top. You can just kind of fold it in half or whatever, but the top is the top, the bottom is the bottom. The plane of the paper makes it impossible for the bottom and top to ever truly switch. So when we look at these compounds in real life, for example, right here, this butene, we'll notice that we can have our carbons on the top and our hydrogens on the bottom, and this may allow for that rotation to be locked because we have that double bond. Furthermore, in this 1,2-dichlorocyclobutane, we notice that we have our chlorines on the bottom, and we can't force them to be on the top. Even if we flip the whole ring, then they'll both be on the top, or they'll both be on the bottom, but we can't change their orientation from one another. So this is what cis-trans isomerism comes from. Cis-trans isomerism comes from that restriction in the bonds. So let's go ahead and look at these two compounds. I've gone ahead and named them 1-chloro-3-methyl-butene. So we have our double bond, we have our chlorine attached to this carbon, and on the other side we have two methyl groups. Now, no matter which structure I take, they are both the same. If I flip the whole thing upside down, there's always a CH3 opposite the CH2Cl. Now, on the other hand, if I add a second chlorine and make it 1,4-dichloro-3-methylbutene, so I've added a chlorine to the top, you'll notice that I can't change these because it will now be different. In fact, the bond here restricts that movement. So when we look at isomerism, this one will not have isomerism. This one will. And that's because to have cis-trans isomerism, we must have two different groups on either side of a carbon-carbon double bond or two different groups on either plane of a ring structure. So let's go ahead and look at that ring structure now after we define this. Cis meaning same, has the same groups on the same side. Trans meaning opposite means the same groups on opposite sides. So we can see that in our example here, these chlorines are on the same side. This is a cis structure. Furthermore, the hydrogens are also on the same side. Meanwhile, over here, our chlorines are on opposite sides, hydrogens are on opposite sides. This is a trans structure. So this is cis 1,4-dichlorobutene. Meanwhile, this other one is trans 1,4-dichlorobutene. So with ring structures, once again, opposite ends is the trans and same end is the cis. So trans 1,2-diiodocyclobutane, we use cyclo to reference it is a ring structure, versus cis 1,2-diiodocyclobutane. Butanes because they are all single bonds. So with this, we can now move on to optical isomerism. I'm sorry that I didn't take notes with you on that first section. Hopefully you were still able to get it, pause it, and go back if need be. So going through optical isomerism, this will be a little more like the normal videos. Remember, as we mentioned way up here, these are chiral carbon centers. So what the heck does that mean? Well, the first thing we have to know is that optical isomerism means that they are non-superimposable. So, for example, non-superimposable just means that we have right and left sides. If I were to take a box and a box, this is superimposable. I can put the box over each other and they're essentially the same. Now, if my drawing was perfect, they would be exactly the same. However, if I were to take a hand, and now you get to witness my terrible drawing skills, and I were to put these over one another, we'll notice that even though they're mirror images, just like the box and the box, they are not the same. The thumbs don't overlap quite right because they're on opposite ends. The pinkies don't overlap right. And you can look at this in your own two hands. So this is what we would call non-superimposable. Well, this is on the left, this is superimposable. This is what it means to have optical isomerism. They are mirror images, yet they are not the same. And so how does this happen? How do we bring in that weird word that I had about chiral centers? Well, let's take a look at a chemical formula first. And I'm going to use a stereochemical formula. So make sure that you remember how to draw these. So I put my hydrogen, I'll put a CH3. I will use a wedge with a bromine and a dash line with a fluorine. Remember, the wedge means coming towards us out of the page up, and the dash means behind the page, out of the page, going back. And now I take another carbon that is literally a mirror image. We will put a dash fluorine, a wedge bromine, and then CH3. These are what we would call optical isomers. This is where we bring the term chiral. Now, what I'm going to do is I'm going to use a lot of terms, and the problem is they all kind of mean the same thing. So chiral, much like superimposable, or sorry, non-superimposable, just means mirror images. It comes from the Greek of hand, because their hands are mirror images. When we look at these two, we call them stereoisomers. Generally, when you hear the word stereoisomer, instead of referring to the cis-trans isomerism, usually people are using it to refer to this optical isomerism. So these are called optical isomers. And a third word we're going to use is enantiomers. Now, one of the hardest parts about this is all three of these mean the same thing. However, stereoisomer can also mean cis-trans isomerism, and all of them will be used interchangeably. So you really have to learn these terms and know what they mean as reference to one another. Now, just to help out a little more, one of the things I like to do is actually look at our stereoisomers or optical isomers or enantiomers from the top down. I find that usually helps me a little bit. When I'm looking at from the top down, I'm going to go ahead and give these all a color code. And I'm going to just leave the carbon and hydrogen as kind of like a central point. Maybe I'll just make it a beam. So when we look at them from the top down, they kind of look like triangles because these are tetrahedrals. That beam straight up just becomes a dot. And we're going to see our blue on the left here, blue on the right here. Oop. F behind the page, and BR in front. When we do this, you can start seeing how they are in fact mirror images, and we can't just plop them on top. Even if we're to rotate them. So now I rotate so that the red matches, the blue and the yellow don't match. If I rotate to make the blue match, the red and yellow don't match. No matter what I do, I cannot get them to fit. And this is kind of what helps you see the optical isomerism or enantiomerism. They are mirror images, but they are not the same compound. They are strictly different. So one of the things that we must learn about is that for a molecule to have enantiomers, there must be a chiral carbon atom. And I put that in quotes because that's another term we need to know. And what's going to make it more confusing is on top of the many terms that mean the same thing up here, stereoisomer, optical isomer, enantiomer, a chiral carbon atom, chiral meaning mirror images, has three other names or two other names that it might be referred to. This may be referred to as an asymmetric carbon Or most commonly, this is referred to as a chiral center or chiral carbon center, but a chiral center. In a chiral carbon atom, an asymmetric carbon, a chiral center, all of these, what that basically means is that carbon is bonded to four different groups. There must be four different things bonded to it. The minute we have any two of the same, this chiral center no longer exists. Now, just because I said there's a lot of terms and I mean it, we're going to use one last term. And I say one last term, but it leads to more. So I apologize for that. When a compound has a chiral center, we actually refer to it. So when a compound has a chiral center, it is what we refer to as optically active, which is where we get the name optical isomers, which we're going to explain why we use the term optically active in just a moment, but we call it optically active. If there is no chiral center, so without chirality, we call it optically inactive. So please make sure you go through this 100 times if you need to learn all these terms. So let's take an example of something that's optically active or something that's optically inactive and see if you can figure it out. So I'm going to take butanol, 2-butanol, or butan-2-ol, sorry, versus pentan-3-ol. One of these is chiral, one of these is not. So one of these is optically active, one of these is not. Please pause the video, take a moment to figure it out. All right, so looking at these, the one on the left has a chiral center. It's right here. The carbon is bonded to a hydroxide. It's bonded to a CH3. It's bonded to a hydrogen, and it's bonded to a well, let's just do the whole thing. CH2CH3. And so we have four different groups surrounding it. Meanwhile, this one has no chiral center. Every carbon is bonded to at least two things that are the same to it. This carbon has 3 hydrogens. This carbon has 2 hydrogens. This carbon has 2 CH2CH3s on either end. And so it is the same and then mirrored on the other side. So there is no chiral center, meaning that the one on the left would be optically active, and the one on the right is optically inactive. To use more terminology, the one on the left has enantiomers or optical isomerism. The one on the right has no enantiomers, no optical isomerism. So why do we call them optical isomers? Well, the reason we do is because enantiomers or optical isomers, oops, spelling is never my strong suit. Enantiomers can be distinguished through their interaction with what we call plane polarized light. So we can use optics to distinguish enantiomers. Enantiomers will have optical activity, and therefore we call them optical isomers. So to figure this out, let's first discuss what the heck plane polarized light is. Like I said, it's a long video. This is light passed through a polarizing lens or polarizing filter, so it only oscillates in one direction. So what the heck does that mean? Well, if we know a little bit of physics, and there's my light bulb, and it produces light, which travels in a ray or a beam. If we like funnel all the light going in one direction, light is both a particle and a wave. As a particle and a wave, it will oscillate. Now, that oscillation doesn't just happen in one direction. Light doesn't travel as a flat path. There's a bunch of different photons, and they will all travel in different directions and oscillate on different planes. Now, this could be like the XY plane or YZ. It doesn't really matter, but they travel in different planes. Due to this nature of light, and actually I'm going to see if I can represent this a little better. If I use a lower, this might add some three-dimensionality to it. Nah, not really. Okay, so it will oscillate in different planes. What we can do is we can set up a polarizing filter, which only allows light of one type of oscillation to pass through. Now, this vertical one is going to possibly allow, I don't know, the red one through. And so the light that we get after the filter only moves in one direction. So what the heck do we do with this? Well, this light is, oops, is passed through a solution with one enantiomer. So either the light or the right or the left version, only one type of that enantiomer. And this happens in a polarimeter, just a device we use for this. And what happens is the light rotates. So it's going to rotate its plane based on the enantiomer. So if we look at this light head on, so if we observe it head on, so here's an eye observing the light, we might be able to see something like this. We start with our light in all directions. I'm going to try and just keep this nice and neat. We take our unpolarized light. It is on all planes. Unpolarized light. And it is on all axes, all planes. And we pass it through a polarizing filter. So once we pass it through that polarizing filter, we now get light in only one direction. And this is what we call our plane polarized light. Then passing it through our enantiomers, we get two options. The enantiomer will rotate this light in one of two directions. So it's either going to rotate it clockwise or counterclockwise. And this will be enantiomer A versus enantiomer B. So each optical isomer will rotate the light the same amount, but in different directions. Each enantiomer rotates rotates light the same amount, but in different, well, I'm going to say opposite directions. And this is why we call them optically active. They can literally change the way the light rotates or change the way the plane that the light moves upon. And so if it doesn't change it, we call it optically inactive, and that's where that comes from. Now, the crazy thing is that if the polarimeter has equal amounts of both enantiomers, well, one's trying to rotate one way, one's trying to rotate the other way, and they're both doing it the same amount, then there is no rotation. And the solution becomes optically inactive. So our enantiomers can appear optically inactive if we have two of the same concentrations. Now, with this, we actually call this solution a racemic mixture. So a racemic mixture just contains equal amounts of both enantiomers. Now, we can use this to actually determine purity of samples because a pure sample of an enantiomer will have a full rotation. Meanwhile, an impure sample will have a partial rotation. So this can be used for analytical techniques or detecting purities of enantiomers if you are making or synthesizing certain compounds that you know have chiral centers. This will become more important as we learn about different types of reactions with organics, such as SN1 and SN2 reactions. So this can also be used in medicine because a lot of medicines that we make do actually contain chiral compounds, and we need to identify which chiral compounds are in the solution. And very specifically, some are active while some are not. So that leads us into the last part of this, which is properties. Now, all you have to know is that other than that optical property, all physical properties are the same. Again, other than optics. Other than optics. For the chemical properties, they're also the same. Chemical properties are similar too. Whoops, I just realized I didn't even spell chemical. Chemical properties are similar as well. But I just mentioned that medicines are very different, and that's because chemical properties are similar, except, and this is our big except when interacting with other chiral molecules. Then they act very different. And one of the things that's chiral molecules are very common in is in the human body. The human body is filled with chiral molecules that interact. When you are smelling something, things like fragrance, your olfactory senses are filled with chiral molecules, meaning enantiomers smell different. Your body breaks down chemicals differently based on whether they are an enantiomer of one kind or another. So it's very important to know that these chiral centers and these chiral carbons can have very different properties in our body, something that we actually utilize in science and medicine all the time. So I hope this super long lesson helps you. I apologize again for the first part that I just kind of read through notes I'd already written, and hopefully you get used to using all these names interchangeably. Otherwise, have a great